Good day. So today we are going to talk about the chapter 2 of electronic devices and circuit theory, which is the diode applications. So we are going to tackle load line analysis, diode configurations, rectifiers, clippers, and clampers, also the Zener diode and voltage multiplier circuits. So for the load line analysis, so a load line is a line drawn on the characteristic curve. So a characteristic curve is this example. This is a graph of current versus the voltage in a nonlinear device like diode or transistor. So here we can see the Q point, which is the intersection point or the operating point, and the load line, the characteristic device, and the IDQ and VDQ. So here to determine the intersections in the load line, we have to use or to apply first the KVL or the Kirchhoff's voltage law in the clockwise direction. So for example, what if we are tasked to find the VDQ and the IDQ of this circuit, which is where gumagamit tayo ng silicon diode that is equivalent to 0.7 volts, and our external voltage will be 10 volts as you can see here, and our resistor is 0.5 kilo ohms. So we're going to find the KVL first. So our KVL, or the Kirchhoff's voltage law, is equal to external voltage minus the VD minus VR, which is all equal to 0. So therefore E is equals to VD plus IDR, which is because voltage is equal to current times the resistor. So now let's go solve for the VD and ID. So for the VD, when ID is equals to 0 amperes, so gagamitin lang natin yung equation kanina. So E is equals to VD plus ID times R. So ID is equals to 0, therefore it is 0. So E is equals to VD. So our E is equals to 10 volts. So our VD is equivalent to 10 volts. So for solving to solve for ID, when VD is equals to 0 volts, same lang din, gagamitin lang equation sa KVL. So E is equals to VD plus IDR, and our VD is 0, so therefore E is equals to IDR, and our ID is equals to E divided by R. So to substitute, 10 volts divided by 0.5 kilo ohms is equals to 20 milliamperes, and this is our ID. And now let's plot what we got from our solutions. Let's plot in the characteristic curve. So here, as we can see in the ID, we have here our 20 milliamperes, and at the VD is the 10 volts. So here we can see the intersection. So we have the intersections at the so we have solved here the IDQ and the VDQ. So the IDQ is 18.5 milliamperes, while the VDQ is equals to 0.78 voltage. So this is the answer, these two. And now let's move to the diode configurations. So let's talk first the series diode configuration. So here we have here the forward bias. As we can see in the circuit, the direction of the polar directions are equal to the direction of the diode, which is still the silicon diode. So ang ginamit pa rin natin is yung silicon diodes, which is equals to 0.7 voltage. So therefore our diode voltage is, or the VD is equal to 0.7 voltage, and also our VD can be equal to we can also say that our VD is equal to E if and only if our external voltage is less than the diode voltage of the silicon, which is 0.7 volts. Now for the ID, or the current of the diode, so ID is just equal to IR. So this is equal to VR divided by the resistor. So knowing that our VR is equal to external voltage minus the VD. And let's move for the reverse bias. So for the reverse bias, the direction of the current is baliktad siya sa polarity. So this is equal to VR equals IR times resistor equals to ID times resistor. So our current is of course equals to 0 kasi nga magiging open circuit siya kasi uh, yung direction is hindi pareho. So therefore our voltage is, our VR will be equal to 0 volts. So now let's move to the parallel configurations. So for the parallel configurations for this circuit, we are still using the silicon diode. So and here we are using two diodes, the D1 and D2. So for our VD will be equal to 0.7 volts since we are using silicon diode. And here we can see that D1 and D2 is parallel, so VD1 and VD2 is equal. And also the V0 is equal to 0.7 volts. So our VR will be equal to 9.3 volts since our VR is equal to external voltage minus VD, and our external voltage is 10 volts. So 10 volts minus 0.7 volts is equals to 9.3 volts. Now to solve for the I1, which is the current flowing to the 0.33 kilo ohms resistor. So we are going to use the KVL. So our KVL will be equal to 10 volts minus the resistor 0.33 times the current, which is I1, minus 0.7 volts, which is the diode voltage. So these are all equal to 0. And to continue, 9.3 volts minus 0.33 times I1 equals 0. 0.33 I1 equals 9.3 volts. And let's divide all with 0.33 ohms. So therefore our I1 is equals to 9.3 volts divided by 0.33 ohms, which is equals to 28.18 milliamperes. So our I1 is equal to 28.18 milliamperes. And for now, we are going to solve the ID1. So note that ID1 is equals to ID2. So our I1 is of course is just equal to ID1 plus ID2. So which means that our I1 is only will be equal to twice the ID1. Knowing that ID1 is equals to ID2. So our ID1 is equal to ID1 I1 divided by 2. So our I1 is 28.18 milliamperes, so this will be divided by 2. Therefore, our ID1 is equal to 14.0.9 milliamperes, which is also a value for the ID2. So now let's move to rectification or rectifier. So rectifier is a device that converts alternating current AC to direct current DC. So it has two types, the half-wave rectification and full wave rectification. So the first type, which is the half wave rectification, converts only 1/2 cycle of the applied AC signal into pulsating DC. So yung half wave rectification kasi is parang kalahati lang yung nakakonvert niya into DC kasi it has yung isang half kasi is nabablock because it only uses one diode. So the direction is allows current only to flow in one direction. And for the peak inverse voltage or PIV or PRV also, which is the peak reverse voltage, so it is the maximum voltage that the diode can withstand during the reverse biased condition. So if the voltage EC applied is more than the PIV, therefore the diode will be destroyed. So dapat yung PIV will be greater than or equal to the peak AC voltage, denoted as VM. Now let's move to the second one, which is the full wave rectification. So this converts the complete cycle of the alternating current to pulsating current, so AC to DC. So yung kanina half wave, so kalahati lang yung kina-convert niya into DC. So dito naman sa full wave is it completely converts the AC to the DC. So this utilizes the full cycle. So it has two classification, the bridge rectifier and the center tap full wave rectifier. So now for the bridge rectifier, so we're going to use 4 diodes that are connected. So yung kanina sa half-wave rectifier, we just used 1 diode. So here, you can see, for the first example, the direction of the voltage direction is equal to the direction of the diode 2 and 3. So therefore, our diode 2 and 3 will be short circuit. So our D1 and D4 will be open circuit. So here, hindi nagsi-zero siya. So, continue pa rin yung current niya to flow. So, sa pangalawa naman, kahit baliktarin natin yung direction, ang magiging open current naman open circuit naman natin is yung D3 and D2. So therefore, which means that yung D1 at D4 naman natin is yun yung magiging short circuit. So therefore, hindi pa din siya magiging zero yung current. So that's why the cycle is completed. So next naman is yung center tap transformer rectifier. So here we are going to use only 2 diodes. So as you can see here, in the first example, the direction of the current is equal to the direction of the diode of the diode 1. So our diode 1 will be short circuit and our D2 will be open circuit. So therefore, hindi siya pa rin nag-zero. So may cycle, may current pa rin na nag-flow. So we can continue to the other one. So the other one, kahit kung babaliktarin naman yung direction, so mag-open circuit lang siya dun sa D1 and yung D2 naman is magiging short circuit. So therefore the cycle is completed. And for the summary of the rectifier circuits, so we can see here the half-wave rectifier is its ideal VDC will be equal to 0.318 volts. So our VM is only means the peak of the AC voltage. And its realistic VDC will be equal to 0.318 volts minus 0.7. Our bridge rectifier will be, its ideal VDC will be 0.636, so twice, it is just twice the half-wave rectifier VDC. So for the realistic VDC, 0.636 volts minus twice the 0.7 volts. So for the center tap transformer rectifier, the VDC is just equal to the bridge rectifier, 0.636 volts, and its realistic VDC will be equal to 0.636 volts minus 0.7 volts.